Hello, sir. This is Dept. Am I audible to you, sir? Sujay, sir. Am I audible to you?
Yeah, I can hear. Yeah.
Okay, thank you, sir. I'm going to start the session, sir. I request Dr. D. Prasad, sir, to chair the session and introduce the speaker to the participants. Dr. D. Prasad, sir, please take over the session.
Thank you, Dr. Sitirami, for inviting me as a chair for the session. And good afternoon. Good afternoon to the speaker and all the participants for today's session. And today we have our guest for the session, Dr. Sujaya Kumar Vishwanath. He received his MSc degree in physics from Sri Venkateswara University, Tirupati, PhD degree in Advanced Materials Engineering from South Korea, Gwangju National University. Dr. Sujaya Kumar is currently working as an Inspired Faculty Fellow at Center for Nanoscience and Engineering at IISc Bangalore. Before joining in IISc, he worked as a research fellow at Material Science and Engineering in Nanyang Technological University, Singapore. His research interests are solution processed electronic materials and devices like transparent conducting electrodes, resistive switching memory devices for neuromorphic computing and physically unclonable functions, etc. And his works are published in high-impact journals like Nature Communications, Scientific Reports, ASC Applied Materials, and Interfaces, etc. Currently, he also working as a guest editor for RSC, Materials Advances and Frontiers in Nanotechnology, on special issue related materials and devices for bio-inspired computing. And the session would go about 1 hour, and speaker would deliver a talk on the title Halide Perovskite-Memristors for Neuromorphic Computing. Yes, sir. Now the session is over to you. You can start the session, sir. Thank you.
Yeah, thank you, sir. Thank you for your kind introduction. Yeah. Can I start?
Yes, sir.
Yes, sir. You can start the session, sir.
Yeah. For network less connectivity, I will go for video mute. Yeah. Okay. Oh, thank you, sir. Thank you for your kind introduction, and I like to thank Professor Thirumal for inviting me for this talk. So today I'm going to present about Halide Perovskite-Memristor for neuromorphic computing. Today's outline is I will try to introduce why bio-inspired computing is important, or neuromorphic computing. What is neuromorphic computing? And I will share the sum of my works on Halide Perovskite-Memristor for neuromorphic computing as well as nociceptors. So if you look at the drivers for next generation electronics, whatever the buzzing words today we are hearing a lot about machine learning and artificial intelligence or natural language processing and autonomous vehicles, they have a common goal to make mission as intelligent as possible to think itself, and by taking little supervision from humans. So now question is where this inspiration came from. So if you look at if you compare the classical computing that we are using currently, like the processors or computers, laptops now generally, with bio-inspired computing, that is computing which happening in a human brain, we will get key insights. So the classical computers, like processor that we are using today, they are good at number crunching and working with data with specific rules, and they can do the ultra fast compared to humans. But whereas in another hand, we are the humans better at the data that doesn't follow hard and set rules. So we are good at recognizing patterns. For example, we can easily identify what is dog face and what is cat face and what is male face and female face. But if you ask the computer or a lab test to identify which is a female face and which is a male face, which is it's like highly impossible. So in a human brain, daily number of neurons and neurons will die. But if any transistor or any component of in a computer will not working, that means that processor will don't work. So by we are more robustic than to the computers that we are using now. So in short, we are good at unstructured data, and computers are very good at structured data. So so now why this is happening? So if you look at the conventional computers that we are using today, the main problem is with architecture. So if you look at the architecture that we are using, we have a processor and a memory unit which are separated by a term we call, I mean like the substance we call bus, where the process is happening at processing unit, and memory will store in another unit, another place. So it is a sequential process. First, the data I have to transfer in analog to digital and digital to analog to do the logic operation here. And we have to change the analog data to digital to store the data. So it's basically sequential process. So if you look at the another hand, if you look at the human brain, where there is no physical separation of processor and also memory. So in human brain we have large number of neurons and synapses. So if you see here, these are the synapses, sorry, these are the neurons, and where the lightning happening, that place is synapse. A synapse is like junction between the two neurons. So, and these are massively connected, and neurons are the processing elements, and synapse is like say memory elements. So basically, they communicate each other with in parallel. So we will call it as a in-memory computing, and also it's like there will be no analog to digital and digital to analog process will happen here. This is like purely analog computing. So this is what the key difference between the classical computers what we are using now and the human brain. So now, what are the current issues with? If you look even more detailed in the issues of current classical computing, we can see there are three defined walls to go further computing. I mean, like in future computing, they are like Moore's law. Moore's law, everyone know, like for every year or every couple of years, the number of transistors in a chip, the IC we are using today in our computers, is increasing dramatically very high. So it's crossing it's crossing number of transistors every year high. So which will define is a Moore's law actually. And what is the memory wall? I just discussed about this particular concept, where we also known as one human bottleneck, where the processor and memory units are separated with a bus. So this is a huge problem again in the architecture way. And heat wall, like if you want to increase the number of transistor in a chip, we have to scale down the transistor. So now we are hearing like from Samsung and even TSMC from Taiwan, they are announced like 1 nanometer, 5 nanometer channel length of the transistor, which is like very thin channel length. So which creates a lot of heat when we interconnect the electrodes for this particular IC. So that to that one, there will be a huge amount of thermal budget will get. So these are the main important three uh, bottlenecks for the future computing with current classical computers. So what are the alternatives? One is like bio-inspired computing, that which we basically inspired from a human brain. So that is the one of the future memory store, and we need a better memory storage. The alternatives are there actually. What are the current implementation of neural networks or the brain inspired computing with exiting transistor technology is like True North from IBM. So this is a company in company who produces ICs and ICs, integrated circuits for computers. Basically, they showed possible to make a human kind of brain with 10 over 16 transistors, and With this number of transistors, they can make 10 over 16 neurons and 10 over 18 synapses. For this particular technology, they use Samsung 28 nanometer process technology. So to implement here, to implement the synapse, they used again 3 capacitors and 2 op amps. So we know one op amp consists of minimum of 15 to 20 transistors. So just imagine if you want to make a human brain which have a 10 over 12 neurons, I mean like 1 billion neurons and 100 trillions of synapses, which are massively connected. Now the technology what we are going here is like very challenging. So even Intel tried with Intel Lohi recently in 21. They also tried with 10 for 19 transistors. They can make 10 over 16 neurons and 10 over 18 synapses with very uh, very recent technology with 10 nanometer process technology of channel length. So this is highly very challenging. So for that one, we need new materials as well as the devices to compute. I mean to make this kind of massive parallel computing. So that brings the memristors for you. So memristors are fourth, these are the missing fundamental circuit element from the fundamental circuit, like along with resistor, capacitor, and inductor. So this was recently, it was invented from, discovered in 1971 from Chuas. So later it was discovered by HP Group in 2008 with the original device. So which consists of like the 2 terminals where dielectric film is sandwiched between those 2, and this is super scalable. I mean we can scale as low as possible, and also it can be scalable as a 3-dimensional structures. So basically it will characterized by a pinch of hysteresis loop. I will explain more about this particular structures in more about the talk. So since I'm working on material point of view for this memristor, so we have a different diversity of memristors. So in terms of material, for example, as I said, this is like very simple structure. We need a top electrode, bottom electrode, and some insulating layer or dielectric layer or switching matrix is required to see the working function of this particular device. So here the top electrode plays a key role. One of the material, one of the flavor of memristor is like electrochemical metallization synapse or memory. So basically here the top electrode plays a key role for this particular memristor. So where top electrode will migrate towards the top electrode on applying the bias, it will migrate towards the bottom electrode and form a conducting filament. I will discuss more about this particular concept. So it will form a conducting filament and change the resistivity will change. So that is what happened here. So another one is like valency chain synapse. So here actually the key is like switching material is the key, and the top electrode should not be like electrochemically active. That means if you apply a bias to a metal or metallic layer, so it should not be oxidized. For example, here if it is a silver, so let me point out. So for example, silver is like one phase. If you apply bias, it will form silver ions and electrons. So like that, this is the top electrode here. But in valency chain synapses, like memory devices, we should not have such kind of top material. I mean like metal electrodes. So basically, it will here only the oxygen or ions will move in these particular devices. So whereas the phase change memory, there is another flavor called phase change memories. Basically, this define the phase change memory will define by the material itself. So if you have the material which can change the phase from amorphous to crystalline phase or crystalline to amorphous phase, basically crystalline phase is like a conducting phase and amorphous is like non-conducting phase. So this here the material is like germanium antimony telluride or germanium based antimony based tellurides are the particular materials we will use to explore for phase change memories. And also the ferroelectric memories are like basically the material should be in ferroelectric nature. For example, hafnia zirconia oxide is now nowadays people are exploring more about that. And redox based memory stores are like it's a basically a polymer which can oxidize and reduce on the bias. So these are the few flavors of memory stores. Whatever the technology we choose, we need materials and devices are the key to make the future computing. So it extends me based on switching characteristics, electrical characterization. We have a non-volatile memory stress. Basically, non-volatile memory stress means if you apply the bias and it will store the memory even if you remove the power. For example, this is the one state which is high resistance state. Basically, high resistance state is the initial state of the memory stress. So after applying the bias, it will set to low resistance state. So this state should be like will be lasting for a long time uh, until unless we apply bias. So on applying the bias, it will reach us to high resistance state. So this is one kind of memristor, and this is like binary memristor. We have two states like R1 and R2, and there is another kind of memristors where we can tune the resistance in number of states. For example, R1, R2. This is like low resistance, high resistance state. This is like middle, like multi-level resistance states. We can say it's analog memristors. And also we have another technology called volatile memristors. Volatile memristors means like this opposite to the non-volatile memristors. Like if you apply voltage and remove the voltage, then the memory will lose. So where non-volatile memories are like it will retain that state. For example, if you are in an on state, it will until unless if you apply the opposite bias to come back its own state, it will retain that state. So whereas volatile memories, when you remove the voltage, it will retain its original state. So this is the volatile memory stress and non-volatile memory stress. These are the different technologies we have currently for neuromorphic computing. So each and every technology have their own advantages and advantages. So I will show binary digital memory stores and analog memory stores and non-volatile memory stores in all different ways. I mean, like where we use these technologies. So this brings to the material point of view. Like I mostly recently I'm working on halide perovskite memory stores. So halide perovskite memories, halide perovskite materials. So basically, halide perovskite material is known for up to solar cell and LED people. So which consists of a ABX3 structure. I will explain more about this in upcoming slides. So here actually this halide perovskite have excellent optoelectronic properties where that's why people from solar cell they are using this material compared to us. Those people are using more actually, and we can tune the band gap just by changing the A site and B site cations. I will tell about this one also, and this is a solution process. I mean, like it hardly need 120 130 degrees C, so to make this kind of material. So it's very low temperature process, and also it's the main is like it has ionic and electronic conductivity, so which can help us to tune the resistive states in these particular devices. So and also we have to understand a lot of unique physics of this particular material which was not explored more. So halide perovskites are like open for research from last few years. So another advantage of this particular materials is like when you compare the synapse and the ion migration in the synapse and as well as ion migration in halide perovskite is like very similar. For example, if you see this biological synapse, like biological synapse, as I said, like this is a neuron and this is one neuron. The junction between these two neurons is a synapse. So here actually the I mean like we store memory in the form of cations like calcium ions and sodium ions. So number of ions penetration from presynaptic neuron to postsynaptic neuron will give you the memory storage. Basically, this is what happened in a human brain. So if you look at this particular memristor, I mean like a halide perovskite, here also same. The halides like iodine will migrate and use a conducting state and non-conducting state. So which is key for neuromorphic computing. This brings me to more about halide perovskites. So halide perovskite basically is like ABX3 structure you can see here. So where this black circles are is A side cation, and this blue is like halides basically, like it can be iodine, chlorine, bromine, anything. It can be any kind of halogen. And B site is like basically lead iodide, lead and tin, and also germanium, etc. We can use different kind of B site cations. So basically, this is the ABXD structure, where A is A site cation is like organic cation. We can organic or inorganic cation. Here, generally people use methyl ammonium, MAPBI3, which is like which is a A site cation here. And you can see this structure where lead, this is the lead iodide, which is in octagonal structure. I mean, like it's like BX3, this is 6, BX6 actually. So if you want to tune this particular material for a band gap, then you have to use A site cation. We can tune with A site cation and also the halogen. If you change the halogen in this particular structure, you can tune the band gap actually. So for example, here actually what these guys are doing is like, if you see, this is the ABX3 structure of 3-dimensional perovskite. So if you want to make it's 2 dimensions to lower dimension, like let me say 1 dimension or 0D, you have to increase the space between this interconnected lead iodides. So if you increase this spatial charge with larger cations, organic cations, then the separation between this octahedral structure will be more. Then basically you are tuning this 3D perovskite to 1-dimensional perovskite or 2-dimensional perovskite. So what we did is like we used initially we started these memristors with methyl ammonium lead iodide, which is basically a 3-dimensional perovskite. So this is the methyl ammonium, which stands as center of the octahedral structure of lead iodides. So where this circle is iodine, and this is the inside the green portion, they have a lead, so which is in a octahedral structure. So initially what we did is like we used MAPBI3 to protect this MAPBI3. We use the PMMA as a polymer which can protect metal with perovskite. So it will avoid the interaction of metal and perovskites. So and also we use P.PSS to protect the same, I2 electrode with the perovskite. So now the structure of this particular memristor is like bottom electrode is IQO and the top electrode is silver actually here, and this is methyl, I mean like 1-dimensional perovskite actually. So to make 1-dimensional perovskite, what we use is like we use pyridinium lead iodide, which is a larger organic cation. So in the molecular dimension, it will be more larger than methyl ammonium. So which separates this lead octahedral structure of lead iodide into a rods basically. You can also see here, actually it forms some rods. This is like 1-dimensional nanomaterial, for instance. So when we compare the switching matrix for this particular two different material, we saw that methyl ammonium lead iodide is like shows very leaky compared to the low dimensional material. So we confirm that low dimensional materials are very suitable for this particular switching to get high on-off ratio. So this is solution process. So what we did is like we deposited on the large area flexible substrate. This is PET ITO, which is 10 by 10 centimeters. So we can deposit in a single spin coating. We can deposit more than 50,000 devices on this particular substrate. So we measured most of the devices. So it was like this shows very good characteristics of memory devices. So actually, I hope you guys also attend the talk from Professor Suranayana. So that's why I'm not speaking more about memristors, how it works actually here. So yeah, this is the memory device which we have done in NTU. So this is published in Nature Communication. So also we characterize the memristors, which can repeat the number of cycles, which is more than 2000 cycles, and also we can retain this memory states from more than 10 or 5 seconds, which is almost a 1.5 day actually, more than 1.5 day. So in the both states, we can retain this particular memory, either it is non-state or off-state. So we also extended this work with crossbar memristor, which are usable, which generally uses in practical applications. So here we use bottom and top silver electrodes with the same memory architecture. So here instead of ITO, what we used is like we used silver. So on the top also we use silver actually. So we made a crossbar memristor with the top silver and bottom silver, and the remaining structure is same. So what we observe is also is like we also observe the similar kind of characteristics, which is like switching high on-off ratio is like 10/6, and also we can measure almost all the devices with particular resistive on-off ratio. So we measured here like more than 56 devices. So all of the devices are showing the similar or comparable resistive switching, comparable resistive switching with other devices. So and also we have to we stimulated this one in a particular way. I mean, in a fashion which showing like NTU. So we switch the devices in N and in the form of T and NU. So we got the say I mean like better on-off ratio, and this shows the reliability of the devices with the different substrates. So it comes to switching mechanism. To understand switching mechanism, what we studied is like we set the devices in on state basically. So that means we are expecting some conducting filament like this by unbiasing of top voltage on top electrode. So basically what we studied is like we studied the low temperature measurements. We studied the from uh, from 200K to 300K, which shows diffusion of when you increase the temperature basically in a metallic conductor, uh, it will the resistivity will get down, or it will resistivity will lose. So here I'm like we observe a similar kind of thing. So what is we find the activation energy for this particular conducting filament, which is around 0.16 electron volt. So which is very comparable with the DFT calculated, iodine activation energy. So this is what we did for to understand the switching mechanism. And also we did the same thing for I mean like we use the same memory devices for neuromorphic computing. So before going to explain what is neuromorphic, I mean like how the device working for neuromorphic computing, I will share what is the key idea we used here actually. So for example, as I said, brain is a network of neurons which are connected with the synapses. For example, here the dotted circles are the neurons and the lines are the synapses. Just assume. So if you have two neurons are activated, like red means it is activated. So then they send the signals to each other like this. And if these signals are very strong, I mean like if two neurons are activated at the same time, the signal will be more strong compared to the previous one. So if it is more strong, we can say we can call it as a phi together and y together. Basically, it is spike timing dependent plasticity, and also we can also know a Hebern rule. So this is the biological term, basically how we store the memory in a human. So similar fashion, actually, I will try to explain even more. For example, a set of neurons are activated by seeing. For suppose if you watching some animal with a weird face and small ears and some pointed face, something like that. So somewhere our mom will say like it's a cat. Then another set of the neurons from another network will activate, and these two networks are connected like this. Then it's easy to identify next time if you saw a cat or a dog. This is what happened when we are a kid. Actually, this is how our mom or a dad will teach learn the things to identify. So before that, no one knows exactly what it is. So like that, a human brain is trained for recognize the faces or different objects. So similarly, what happens with spike timing dependent plasticity is like, so we have a presynaptic neuron and also postsynaptic neuron. As I said, like synapse is a junction between two neurons. So if you apply the pulse or action potential on a presynaptic neuron, and also we apply a pulse on postsynaptic neuron, if these two pulses comes one after another, for example, presynaptic neuron pulse will comes after the postsynaptic neuron, then we will call it as a potentiation. So if this timing of these two pulses is very less, then the potentiation will be more. So if it is less, so the potentiation will be less. So like that. So if you apply, if postsynaptic neuron pulse will come before the presynaptic neuron, then we call as a depression. That means basically we are forgetting the things. Uh, Basically we are forgetting the things. That is how a human brain works. No, this is how actually I mean, like, human brain also was observed while conducting experiments on human brain, or how the synapses or neuron works is like very similar fashion. So we try to implement this kind of studies on our device. So what we did is like, we assume that the top electrode is a presynaptic neuron and bottom electrode is a postsynaptic neuron. So we applied the same pulses, so similar kind of pulse. So this is, you can see here, the 1 volt pulse, and after negative pulse in a waveform, such a way to activate the ion migration in this particular device. So we use a different pulses here. So one is on top and another is bottom. So what we observe, like when we apply the pulses before and after, we got the potentiation and also depression. So what we observe is like same. The similar fashion we also observed in our devices. That means we are trying to emulate the device. We are trying to emulate the human brain kind of mechanism through our device. So if you see, I mean, like in introduction, I showed this particular image to make a synapse. Actually, they need three capacitors and two op amps. So basically, to emulate this kind of mechanism, they use this many devices actually. So here we actually reduce the number of devices to one, and we can try to emulate the biological function, what human brain or a synapse can do. So this is what we did from our device point of view, and we extended this with pattern recognition. Basically, this is like analog neural network. I mean, this is a spiking neural networks. So basically, this is artificial neural networks. So which have an input layer and also output layer, and there will be hidden layers. So generally, what we do is like we give the image or a pattern to the input layer, and this image is transferred to the hidden layers by a feed forward way. So then this image is like, it will converge to every hidden layer and every synapse and a neuron uh, to recognize the better, and we need to train this particular images. So then you can finally obtain a image what we input that image to get the output. So what is the output we got is like, when we use the less number of neurons in our circuit, actually we got only less than 10%. When you use increase the number of neurons more than a 50, we got more than 70, and also we reached up to 80, 85, 82% of pattern recognition in this particular way. So we use on 1,000 trainings, we got less number of diseases were recognized here, but after 6,000 training cycles, most of the devices, like, we can able to recognize from this particular device by using this particular device. So the accuracy is also increased to 80% after a number of sample trainings. That means 6,000, after 6,000 trainings, we got the digit recognition more than 80%. So yeah, this is how non-volatile memories can be used for neuromorphic computing for neuromorphic computing. Now I brings to nociceptor, which is basically made with volatile memory devices. As I said, volatile memory devices are like it cannot retain its memory or the previous state if the power is removed. So it basically it retains its original state. If you remove the power, then basically it will retain its original state. So with this one, actually, we also tried with perovskite material here with top electrode silver and bottom electrode is ITO. This is a flexible ITO basically. And same structure we use, we have to protect this polymer, this perovskite from the metal electrodes, because perovskite can react with metal. So to avoid the situation, actually we protect this perovskite with two different polymers. So what we see is like we apply the potential voltage, so we can see device is set to some on state, but immediately when you remove the potential, the voltage, it comes to its original state. So this is we also known as threshold switch or non-volatile switch. So this particular technology have a very good advantage. That is like generally we use it as a nociceptor. Basically, nociceptor is it's in basically exists in a skin, so where you can feel the pain basically. So for example, how it works, if you put your hand on a hot surface, so nociceptor uh, in your skin can be damaged, and that damage or the heart will be a action potential. Basically it will send the signals to the neurons in your skin, neurons in your brain. So when action potential causes neurons to release then the neurons in our brain will release the chemical across the gaps in the synapse, which can happen across the number of neurons until the brain receives the information. Then after receiving the brain information was received from the brain, then immediately you will take up your hand from that hot surface. Basically, this is like a neuron in your hand is kind of a receptor actually. It can receive the pain. I mean, like you generally feel pain actually when when you pinch the your skin. Still, you can feel if someone is slapping you, you can feel the pain. So this kind of respirators, receptors can be made from this particular memory technology. So we can also why we are making this kind of technology means like we can use this technology for robotics. So recently we are the robotic applications are expanding a lot in like industries, battlefields, and also space in the space missions actually exactly. So instead of sending a human to the space, we can send a robot which can feel the atmosphere effect. I mean, like kind of a gas or the temperature or that particular planet. Instead of sending the human, we can send the robots in the future. So that's why this particular technology is more important. I mean, like to develop. So we studied the characteristics of nociceptor. So what is nociceptor characteristics is like sensation. First, how I mean, like if you keep your hand for a long time here, I mean, like for a minute, you won't feel any sensation. If you put the hand on a hot surface for a long time, then you start feeling the pain or the heat effect. So like that, we also try to emulate such kind of uh, such kind of characteristics from our device. So here the sensation we gave is with the potential voltage pulses. Actually, when you give lower voltages like 0.2 or 0.5, device won't work. Device not showing. I mean, like still we can retain that particular stimuli. So here, I mean, like after 1 point, I mean, like zero point 0.7 volts or 0.8 volts, we can feel the sensation of this particular, the stimuli what we applied here. So we also studied another characteristics, like we are basically optimizing what kind of sensation we can see from our device. So basically we studied different kind of sensations here with different magnitude of the voltage pulses. So as we change the voltage magnitude, you can see the pain. I mean, like here current represents the pain actually. So if you keep your hand for a long time on a hot surface, basically you will start start feeling the effect of that particular temperature. That is what here we try to see. So here is like what we say is a relaxation. So even if you got hurt, so after a particular time, you won't feel any pain. So if you, for example, if someone is hit you, you will feel a particular, I mean, like very less time you can feel the pain. So if over a time, you won't feel any pain from that instant or that particular sensation. So that's what we studied here actually. So here our device can feel the pain in a particular time after 1.5 second, 1 second, 1 second, we won't feel anything. So that is what our device is here do. So we tried with the same kind of sensation and relaxation with different kind of pulses. So like let me say 0.75, 0.85 and 1 volt. So we can feel different sensation timing for different pulses. So this all will help to understand, to integrate this particular device to robotics, which can feel pain. So that is what we have been. So in biological word, we can say adalonia and hyperology are the specific terminology we want to use. For example, what is hyperology is generally it will feel the sensation reducing the threshold. And also what is hyperology is like it feel the intensify the signal. Basically if it is more, you can see with particular after the particular damage of this volt, we will see the pain will increase every time. So that is what is the story is about. So yeah, with these two technologies, what we did is like with Perovskite-Memristors, we can able to make memory devices as well as neuromorphic computing as well as nociceptor for robotic applications. Okay, thank you. This is my end of the talk, and I like to thank the DST for giving me INSPIRE faculty position, and also some of the work was done at Nanyang Technology University, Singapore. So I have to thank them. Yeah, and also I like to thank the Tirmal sir for inviting me for these talks. Thank you. If any questions, I can happy to take.
Yeah. Dr. Sudhir, sir, can you hear me?
Yeah, sir, please.
Yeah. So truly it was fascinating stuff. Nowadays, the whole world is turning out to be artificial intelligence and machine learning and also neural networks.
Mm-hmm.
And it was undoubtedly a fascinating talk, enlightening all the people in the audience getting connected to next generation electronics,
Mm-hmm.
and also making us to think of the classical and the bio-inspired computing as well. And you addressed well the issues with classical computing and its hardware in this big data era.
Mm-hmm.
And also the need or the necessity of new materials and the devices and their crucial role well explained in this talk. So it's a truly fascinating stuff.
Thank you,
And
sir.
before I ask the audience, before I open up the section for questions,
Mm-hmm.
I have a fundamental question that's related to on a large scale or broader scale
Mm-hmm.
fabrication.
Mm-hmm.
We're all actually going to deal with biomaterials, right?
Yeah.
So all biomaterials, they do have some, they do have their own nature-related issues, challenges. So when we think of the device level,
Mm-hmm.
or what should I say, the assembly level,
Mm-hmm.
how do we, I mean, what kind of challenge we do have in terms of sustaining the nature of these biomaterials? What are the challenges involved in making them used for a long time? Because when they get exposed to temperature gradients, they will be definitely, lose their nature, will be denaturized.
Yeah,
So
yeah,
what are the
that's
things involved in this context? Can you please throw some light on this?
sure, sure. Thank you, thank you. So the question is about like why we can't use biomaterials, right? That is what the question. What I understood.
We do use, but how do we sustain the nature of these biomaterials in different temperature conditions?
Yeah, that's interesting question actually. So see, the reason why we choose the halide perovskites is like is it we can switch that particular this material or this material kind of devices in a particular low voltages. Like we have to reduce. I mean, like the if you see the human brain, what is it? Okay, just a minute. Yeah. So the power, the main reason why we choose the different material is like the yeah, the power consumption from the electronic devices is very huge. If you want to make this kind of massive human brain, so that is one reason why we always have to choose the biomaterials or material which can switch or which can operate under the low voltages or low power. So that is one reason. And if you are talking about reliability, yeah, of course, reliability is there is a big challenge. I mean, like we have to test the devices with different kind of temperatures. So I mean, like the one of the way what we are trying this particular material is like we are encapsulating this perovskite with the polymers which can stable over the 100 plus degrees C. I mean, like let me say 200 degrees C. This PMMA, or we have a kind of a polymer which can stable for that particular voltages. Sorry, the temperatures. So like that we can look forward for this this kind of devices for in future. And I'm not telling that we can make a IC from this kind of material, but we can use these materials for this kind of material or devices for edge computing. For example, if you need a sensor which can have to work. For example, I explained the robotic skin. Basically, the sensors are interconnected to these memory devices. So those kind of technology can be made with biomaterials and bio. Yeah, that is what I think I answered you. What?
Yes, I got the answer through
Yeah,
your entire
yeah.
wonderful sir.
Yeah.
Now, it would be nice if we take any couple of questions from audience. Yes, Dr. Sudhir, yeah, we are extremely happy and delighted having you here for this talk. And thank you very much. Thank you all.
Thank you, sir. Thank you very much.
With this, we can conclude the session, sir.
Hello?
Yes, sir, if you can. Go ahead, sir. Go ahead. Sudhir, sir, can you hear us?
Yeah. I can hear. Yeah.
Austin has some doubts, sir.
We have
Yeah,
one
sure,
question over here, sir.
Yeah, sure.
Good afternoon. Sir, good afternoon, sir. Are you able to hear me, sir?
Yes, I can hear. I can hear you.
Actually, my question is, so this is, can we apply the same technology in an inverse way? Reciprocal, yes. From brain
Come again. Same technology.
technology in a reverse way, reverse process. It is input is going to brain.
Input is
going to the brain now from the biomaterial.
I'm not really getting the question clarity clearly. Is it like you wanna probe the human brain, something like that? You are asking?
Yeah, exactly.
Uh, Actually, we can try. I mean, some of the people at MIT they are trying, but it's just basically they are trying to understand how human brain is working. So whatever I showed today is like just one characteristic. Basically, we are still no one know how human brain store the information. This is one
Yes.
of the it's like earlier work what people have tried to understand how the human can remember and forget the things. For example, if you read one or two times you won't remember, but if you read many times a particular thing you can retain a long time. So something like that, people try to understand what exactly human brain is doing, because we can do what lot of things by eating one meal, but that is very less power compared to what the power we are using for the computers. So still we can implement basically to understand the human brain, but not the technology, I feel. Yeah, I mean, like out from by implementing this particular technology in human brain, it's a long way to go. Yeah, I'm sure. Yeah.
Yeah, one more question.
Yeah, one more question.
Good afternoon, Suresh sir. Actually, I
Yeah.
have a question. I've been hearing you from a while. Really, your concept is very innovative.
Thank you.
But uh, I just want to know that
Speak loudly.
give me
Talk loudly. Stand up.
Keep your mic closer to the mouth. Hold it properly. Hold your mic properly.
I've been hearing about this concept for a while. I understood few things. Actually, it's very innovative and fascinating, and I feel like it's has an impact on the future. But I just want to know, just tell me briefly that what the difference and the value it adds to the world.
Yeah, is your question like what is the current? Okay, so the question is how this is very conceptual and informative, but how it's going to be connected with the future perspective.
Ah, yeah, that's a good question actually. If you so this like see whatever you are using. I mean, like, can I know what mobile you are using currently?
It is Redmi.
Sorry.
Redmi.
Yeah, see, I mean, like, in when I'm doing my masters, actually, even I don't have any smartphone. So even I never thought that we are going to use a smartphone. The technology was is simply basic thing is like where the IC, I mean, like integrated circuit was implemented such a good way. The transistor scaling is like went very down to 10 nanometer process technology, like currently iPhone and those things are using. I mean, like this technology is like we are using for information, I mean, like basically communication, internet of things. So if you have this kind of technology like bio inspired or new human brain inspired kind of technology, basically you can reduce the workload. You can do whatever you wanna do by mission actually. So that is the future. I'm talking about more than 100 years. But if we have the chips with this particular device technology, maybe we will get more handmade. I mean, like what I can say. This particular technology will help you to reduce the cost of your mobiles, or yeah, I mean, like the electronic things. Basically, it will reduce the cost, and we'll use it for more kind of applications.
Hope it answered you. Yeah. Are there any other questions from audience? Yes, I think no questions, sir. So that's all, sir.
Yeah.
Thank you for joining us once again. I hope we can conclude the session. Yeah. Yeah. Yes, we have another session now. Dr. T. Vishwam, sir, are you there? T. Vishwam, sir.
Yes, sir, I'm audible.
Yes, sir. Yeah.
My voice is clear now. I'm clear.
Yes, sir. Everything is clear. Sir,
Fine.
You should share your share the screen, sir. Slides as well.
Sir, your voice is not audible to me.
So you can present your.
Yeah, fine. Yeah, fine. 1 minute. 1 minute.
Sir, you are muted.
No, I'm incorrect. 1 minute. Come on. Yeah, one. Are you able to see my screen? Are you able to see my screen?
Not yet. Not yet, sir.
1 minute. Is it okay now?
Yes, sir. It's getting done. Yeah.
Fine. So can I start my lecture now?
Just a moment, sir.
Oh, fine.
Sir, I'm delighted to chair the session. And audience, we are going to have another session now from Dr. T. Vishwam, Dr. Vishwam Taloju. He is currently working as assistant professor in the Department of Physics, Dept University, Hyderabad campus. He did his PhD in the Physics Department, Indian Institute of Technology, Madras. He is passionate about teaching scientific concepts, fundamentals, principles, and how the things work, present electronic gadgets, instruments, etc., to undergraduate and engineering students. The aim of education is to teach students how to think rather than what to think. The passion to teach students and enlighten them with topics of their interest is the driving force behind his experience as a teacher. The practical applicability of the topics he teaches in the classroom is a constant force to make the students explore the possible areas of research. He will also encourage students to update themselves with the latest trends in emerging areas of study. This is possibly only through the upgradation of the existing knowledge in any field. Hence, providing the students with a comfortable environment to work in and seeing them implement new method motivates him to introduce the latest trends in science and technology in his classroom. To enhance the learning in the classroom, he uses group activities and discussion forums, which enable him to reach out to every student in the classroom. In addition, to ensure that the students are aware of the latest trends in the field of physics and also material science, experts from different fields are invited for lectures and interactions with the students. Apart from regular teaching, he has also published more than 45 research papers in reputed international and national journals, one patent, one book chapter, and presented the research outputs in international and national conferences. Recently, he had received a project from DST as a co-investigator and has applied for a future for project under CCR scheme to DST India. To give back and contribute whatever he can to do the society, he is currently involved in teaching basic principles of physics to the government school students through the learning aids and conducting scientific exhibitions. So we are delighted to have him for the session, and he's going to deliver a talk. It will be about 1 hour, and the title is going to be Microwave Dielectric Measurement Techniques. Thank you, sir. We can start the session now.
Thank you, sir. Please tell me that my voice is audible or not. Is proper, sir? My voice is clear to you, everyone? My voice is clear?
Absolutely, sir. It's very clear.
Yeah, fine, sir. Okay, fine, sir. So, yeah, fine, sir. If any problem is there, just interrupt me so that I can check my mic. Yeah. So I hope my name is Vishwam. I'm present as a faculty in Geetham University. So you have lunch. So I'm able to teach the concept to you. Especially my lecture is planned based on the BTech students, little bit applications, then followed by the research point of view. So I hope you're not like this, right? So because you have the heavy lunch, definitely you'll get sleep. So I'll make you somewhat interesting in this lecture. I'll ask you some questions. I'll try to show a live demonstration so that you're able to understand the concept clearly. I would like to present my topic, what in by dielectric materials and how you're able to measure certain properties, especially in the microwave frequency region. I have planned my talk like this. What exactly the fundamentals of dielectric materials, what in by dipole moment, what type of polarizability, how this polarizability depends on frequency, why we are specific about microwave frequencies, and what are the parameters we can obtain from the microwave, how can be useful for certain sensor applications. So after completion of these topics, I'll ask you some questions to you. So please give me your opinion, yes or no. So I want to justify the talk. I'll show some videos related to the topics. After that, how to characterize in the microwave frequency region. So I divided into the three segments. What's the low frequency region, mid frequency region. So after getting the data, what you can calculate, how it is useful to develop any sensor type of things. I'll show my research areas related to the biological liquids, how I'm going to use this particular mechanism properties to analyze certain material properties, some of the important, some published results. So let us start with the basic fundamentals. So here the dielectrics are insulating materials, but not insulators or dielectric materials. Here I'll take you one example to explain you how the insulators are differ from the dielectrics. So dielectric materials consist of bound charges, whereas insulators does not consist of bound charges. So due to these bound charges, it executes a dipole moment. If I take one example, wood is an insulator, but it's not a dielectric material. If you take a Teflon, glass, mica, quartz, these are all the things related to the dielectrics. But so the wood is insulated but not a dielectric materials. But the Teflon, what these are the dielectric materials and come insulators. So they are poor conductors of electricity. So these electric materials are poor conductors of electricity. So due to the bound charges, when you apply certain amount of charge, so these dipoles get displaced, the charges get displaced, constitutes a dipole moment. So in intermediate, you have studied that the dipole moment is nothing but two equal and opposite charges separated by a smaller distance. So here minus q charge and plus q charge are separated by a smaller distance. So it is said to be the dipole moment. So the dipole moment is a vector quantity. The unit of dipole moment is you can write in a MK system, Coulomb meter, whereas in the case of CGS system, it is said to be the debye. So if you look at this in the dielectric, based on these bound charges, the materials can be classified into the three categories. One is polar materials, which consist of a permanent dipole moment. The meaning of a polar material is nothing but it possesses asymmetrical charge distribution, so it constitutes a dipole moment. The best example is a water. So because the water doesn't have the proper symmetry, so it possesses certain charge, maybe the hydrogen and oxygen. So it constitutes a dipole moment. If you consider a non-polar material like a benzene, ceramic plate, maybe oil, and carbon dioxide, where the structure is a linear, so the net dipole moment is going to be cancelled, so that there is no dipole moment. That materials are said to be the non-polar materials. Example, our body is a polar material. Next one is induced dipole moment. The meaning of induced is either you have to apply certain external force to separate the charges. Example, if you take a piezoelectric material like a quartz, when you apply certain pressure, so it induces a dipoles and charges in a perpendicular manner. So it creates an electric field. So this type of materials are said to be the induced dipole moment materials. Other category is nothing but a temporary dipole moment, especially for polymer materials with respect to the frequency, they exhibit certain dipole moment in that region. So this type of materials are said to be the temporary dipole moment materials. This occurs only in the case of dispersion region. So here, in the case of dielectrics, we are talking about the polarization. A polarization nothing but suppose in an auditorium there are maybe consider 100 people are there. If 100 people are attending my class in a concentration, I can say that I'm polarized you. I'm polarization because you're listening my class. If some of the people are not able to listen, so that you're not polarized. So within the auditorium, it has certain volume. So when you apply certain external field, giving my lecture, so that you're all listening my lecture. So I'm polarizing you with respect to my direction. So here, a polarization is a macroscopic quantity defined as number of dipole moments per unit volume. Here, each and every dipole is a microscopic quantity which produces a dipole moment. So in general, the main use of dielectric materials are nothing but to store the electric field energy. If you recollect your basic knowledge in intermediate, we talk about dielectric constant. So dielectric constant is nothing but we can define like capacitance in the medium to the capacitance in the air medium, or electric field in the medium to the electric field in the free space. Here, if you take the capacitive material, if you introduce a dielectric material, so that there's inducer charges which will be developed. So due to the inducer charges, there is a Q is increases, so that capacitance is going to be increased. Here, in the case of dipoles, here we're calling this a dipole moment. A dipole moment is nothing but two equal and opposite charges are separated by a smaller distance. When you apply an electric field, they polarized with respect to one direction. Here, dipole moment is directly proportional to the electric field. This is said to be the polarizability. The polarizability is a microscopic quantity. Polarization is a microscopic quantity, and dipole moment is a microscopic quantity. So the outer layer, if you consider the outer layer, the dielectric constant, susceptibility, polarization are the macroscopic. The microscopic variables are polarizability and dipole moment. So in the case of a, we have the relation between the dielectric constant versus polarizability. The dielectric constant is a microscopic quantity, is directly proportional to the polarizability. So the Clausius-Musatti equation says that if you consider any material inside the dielectric, it possesses certain polarization. That polarization related to the susceptibility, and susceptibility related to the dielectric constant. Now, my complete macroscopic variables depends on the microscopic variables like polarizability and dipole moment. I will tell you the example of this, what is the air medium, non-polar medium and polar medium after 2 slides. So in the case of, because you are confused with the dielectric constant, then the complex dielectric constant. Remember students, if you operated only for static frequency region, there we're calling as a dielectric constant. But when the same material is operated for high frequency region, the dielectric constant is said to be the complex permittivity. In the case of complex permittivity, it becomes a complex number. Why it becomes a complex number? Because if you recollect your intermediate basics or BSc first year, you talked about the polarization, you talk about the electric field. Since the polarization vector is in accordance with the applied voltage, so that there is a phase lag between the dipoles and the applied electric field. So it constitutes a phase lag. That phase lag makes the dielectric constant in a complex quantity. So here the epsilon prime represents the storage of electrical energy, and double prime represents the energy loss in the form of a heat. So this is set up the complex because in especially in the microwave frequency region, we are talking about the complex permittivity. So when you understand in terms of optical frequency region, there you can represent like a plus. The plus in the sense that the energy is released in the form of light, whereas in the case of microwave frequency region, the energy is absorbed, it released in the form of a heat. So please remember this complex permittivity. I'm trying to give you one video related to this. So I said just now polarizability. This polarizability is a three categories with respect to the frequency because I'm concerned about the microwave polarizability, the dipolar polarizability. To understand this particular concept, I have made a small animation here which shows that these water molecules are rotating from one equilibrium position to other equilibrium position. So this water molecule, the rotational frequency is matching with the microwave frequency region. It creates certain heating mechanism. That is what the principle of microwave oven. This polarization is inversely proportional to the temperature. So my polarization depends upon the frequency and inversely proportional to the temperature. So it appears in the region of gigahertz region. If you come to the ionic polarizability, please look at this particular diagram. So this molecule starts vibrating like a spring forces, especially in the sodium chloride crystal. When you apply an electric field, the positive charges and negative charges starts vibrating. So the ionic polarizability is called as vibrational polarizability, which occurs in the case of infrared region around 10 to the power of 12 hertz, whereas microwave 10 to the power of 9, this is 10 to the power of 12. The next category is the electronic polarizability, which is occur in the case of especially for optic materials. When you apply the electric field, there is a displacement of positive charge and negative charge, which constitutes a dipole moment. That is said to be the electronic polarizability. Remember, among the three polarizabilities, the dipolar polarizability inversely proportional to the temperature and depends upon frequency, whereas ionic, electronic does not depends on temperature. Please make sure about this particular point. Now, this is a plot related to the non-polar and polar material. Let me take one example. Let me take some volume. All the dipoles are oriented in the field direction. Let me say this is the dipoles are oriented in the field direction. So these dipoles get oriented in the direction of field. Now when applying a temperature to this temperature is what happens, this temperature is depolarizing these dipoles. So due to this temperature, these dipoles get oriented in the random direction like this. So if the dipoles get random with respect to the temperature, my polarization is decreased. So once the polarization is decreased, my dielectric constant is decreased. So the CH3Cl is nothing but a polar material. In that case, my dipole moment value is decreased, then the dielectric constant is decreased. So here I'm plotting with respect to 1 by T. So this is said to be the polar, this is said to be the non-polar. Why the non-polar graph is straight? Because it does not possess any dipoles. They are independent of temperature. So let me look at this one. To explain this particular topic, I'll ask you one simple question to you. Uh, can we get ring when we keep our mobile phone in a metal box? Please, anyone, can you answer this question? Students? Sir, I'm audible, right? Sir, I'm audible, right? Yeah. You ask your students, can we get the ring when we keep our mobile phone in a metal box?
Anybody can answer that question?
Just give a thought about it.
Yeah, please, yes or no. Please speak.
Say yes or no.
Sir, one student is going to answer your question.
Yeah, fine. Okay, fine. Good.
Probably
Yes or no?
Probably yes.
Probably yes. Okay, I'll show you no. Look at this video. Let's see the video. Let us relate this concept to our understanding. So this is the video done by one of my student in the class. So please observe this video, and most of the people who said answer yes. So that answer, let us check yes or no by looking at this video. So you can try this small exercise after going to your home. Is it okay, everyone? Is it okay, everyone? Is it yes or no now? Please give me the answer.
Same.
Okay. So we have seen the video. We understood something so that the electromagnetic waves cannot penetrate from the metal surface. It get reflected from the surface. So you have seen the video. Let us understand the physics involved in that. If you look back, so here, what exactly to interpret the result? We know that electromagnetic wave, so it's a sinusoidal waveform. So I written the electric field in this because in that the atoms get vibrated. So I have to consider this particular equation, F is equal to QE. So this is the force, m into a d square x by dt square into the electric field multiplied with the charge. So this is the differential equation. If you elaborate this in further manner, finally I'll get some relation here. My dielectric constant related to the 1 minus of some parameter here. This is said to be the plasma frequency. This is said to be the plasma frequency. At low frequency region, let us consider a metal blocks. All the charged particle there on the surface, it starts vibrating. So when any electromagnetic wave is comes and hit this particular surface, this plasma frequency does not allow because my incoming energy is very lesser than the plasma frequency energy. So it get reflected back. If my instant energy is greater than that infrared region or visible region, like take gamma rays, X-rays, they can penetrate from the metal surface. So this particular graph explains about the reflectivity versus frequency. So below the plasma frequency region, that visible light get reflected. Above the plasma frequency region, like gamma rays, they can penetrate. To understand this particular complicated theoretical part, I have shown a small video related to this. So by looking at the video, you understand that the visible light, the microwaves cannot penetrate from the metal box. The gamma rays and X-rays can penetrate from this. I hope the concept is clear to you, everyone. I hope this concept is clear so that I can go move further. Yes, clear, right, everyone? Okay, so let me go for the next part. So this is the complex permittivity versus frequency. Look at this. The dielectric constant is decreasing with increase in frequency. The first part is set with the dipolar, the rotational polarizability. The next one is vibration polarizability. This is the optical polarizability or electronic polarizability. Remember one thing, I'm focused more about the double prime. This is set with the loss. This curve shows the loss. Why I'm preferring loss? I'll let you know after 2 or 3 minutes. So why I'm going for microwaves? Because why it is called microwaves? Because the frequency is in terms of 10 to the power of 9 hertz. Why it is called microwaves? Because if you consider with respect to the wavelength in terms of millimeters, so that is the reason it is said to be the microwaves. So if you look at the electromagnetic spectrum, this is the radio waves, microwaves, visible, then infrared, ultraviolet, X-rays, and gamma rays. My specific area is microwaves. My area is in the microwaves region, which is set with the gigahertz region. So this is the radio waves. So here, everyone understand that, okay, microwave is a radiation. What exactly the radiation? So radiation is defined as emission and propagation of every energy through a material or substance in the form of a particles or waves. This radiation may be two categories, non-ionizing radiation and ionizing radiation. This non-ionizing radiation is nothing but the microwave, infrared, and UV. These particular waves can change the properties of the electromagnetic wave in terms of wavelength. Whereas in the case of ionization energy, they are the shorter wavelength, so it got radiation, it disturbs the structure. That is the reason the ionizing radiation is harms the peripheral because of gamma rays, X-rays, they are killing the inside molecular structure. So we are in the range of non-ionizing radiation. So I'll tell you a small example. There's a Percy Spencer who discovered the microwave oven. So when he's working the Bell Laboratories, he had a candy in your pocket. When he's doing this for certain microwave experiment, he suddenly observed that this candy got melted. So what exactly, why the reason behind why the candy got melted? So he tried number of times, the same result is obtained. He tried with different materials like a polar and non-polar materials. He observed that okay, something radiation related to the this particular melting of the material. So what he understood that the frequency, the electromagnetic wave frequency of 2.45 gigahertz, it is something related to the resonant frequency of the water molecules. So here, this is the water molecules. This particular frequency of incoming radiation and water molecular rotational frequency is exactly matching. So there is a concept called resonance. So due to the resonance, the energy released in the form of a heating. So here, the micro working principle is nothing but the resonating phenomena. The rotational frequency of the water molecule is exactly matching with the incoming frequency. So you're able to understand the dielectric heating. So this is what the principle of microwave oven. So the energy is absorbed, the energy released in the form of a heat. So due to that reason, the material get cooked up. Anyone knows what is the first material cooked in the microwave oven? Audience, what is the first material cooked in the microwave oven? Anyone? Anyone? Audience? Anyone? Anyone? It is a popcorn. The first one is a popcorn. Okay. Initially, this microwave oven name is nothing but radar range. So it's a bigger size like a room. Finally, it came into the small box like this nowadays. So look at this. Can we heat the water in microwave oven? Audience, students? Yes or no? Anyone? Can we heat the water in microwave oven?
Sir, answers are yes, sir. Mostly.
Oh, you said everyone yes. Very good. The answer is yes. So let me ask one more question to you. Can we heat the oil in microwave oven?
Answer is no, sir. Majority.
Answer is no. So may you know the reason why? May you know the reason why we cannot cook the microwave oil in microwave oven? Anyone? Anyone? Can we heat the oil in microwave oven? Anyone try? Okay, I'll give the answer. Because oil is a non-polar compound which does not possess dipoles, so the independent of frequency, so the energy cannot be absorbed. Because why the water got heated? Because just now I said that in the microwave heating, the incoming microwave frequency of 2.45 gigahertz, the rotational frequency of the water molecule is at 2.45 gigahertz, so there is a resonance. In the case of oil, so this oil resonating frequency is different and incoming frequency is different, so there is no matching. So that is the reason we cannot cook the oil in microwave oven. So I'll ask you one more question now. Can we cook egg in microwave oven?
Sir, majority yes, sir.
Majority yes. How many of you tried or just like guessing the answer? How many of you tried? How many of you gone through the manual of microwave oven? Any response? Okay. So I'll show one video to you just now, which I have done. Look at the video. You see, you have learned today that we cannot cook the egg in the microwave oven. I'll show you a small demonstration here. Look at this. I've taken the egg, I put in the microwave oven. Let me see this. Yeah. Anyone can explain that why it is burst like anything? I operated only for maximum around less than 2 seconds. Anyone?
Yes, students. The
Anyone?
answer may be right or wrong. What you guess, you can give a response.
You can try if you keep egg in the water also, you put in the microwave oven. Maybe it may take another one more second to burst it out. We cannot cook the egg in the microwave oven. Why? Because is a you can see that in the conventional way we can cook the egg, but in the microwave oven, just now said that it is a concept of internal heating. This internal heating develops a radiation pressure. So because it is the adiabatic process, the energy is generated within a shorter time so that it cannot able to cooperate with the surroundings. The radiation pressure is more than the outside, so it starts bursting. So to explain the radiation pressure, I'll show you one more video. So I've taken the grape, I took the grape. I want to see that how the radiation pressure is coming out. Please observe this. You're able to understand this concept clearly because I'm talking about radiation pressure. Look at this. So this is the radiation pressure. So because it's a polar material, when the molecule starts rotating, it creates a pressure, the more heat energy inside, so that pressure is coming out from the jet. So there is no scope in the case of this particular mechanism egg. The radiation pressure is more. That pressure, because of rotation of the dipoles, internal heating, because of the heavy pressure, it starts bursting out. So please don't try this experiment in your home. I've shown the video because it completely makes the nonsense thing. Better don't do this. So this is about the microwave oven. So let us come to the frequency measurements. Here I'm talking about the static. When you talk about the static, I'll talk about the dielectric constant. So especially for a solid or liquid, we are measuring the capacitance with the material, without the material. So this is the cell. So inner wall, and this is the outer layer, this is the inner layer, the inner cylinder and outer cylinder. In between, I'm keeping the liquid. So if you measure the capacitance in the liquid medium and write out the sample without liquid, measure the capacitance, that will give the ratio, will give the dielectric constant. So you can do this experiment initially in your laboratories. The BTech laboratory we have. This is for liquid. Similarly, we can do this part for the solid samples also. So this is the experiment set up for the solids. Make a pellet. So measure the capacitance with the material, without the material. So we can calculate the capacitance of the material. From that, you can calculate the dielectric constant, provided you should have area and thickness properly. This is about the static measurements. So for especially for higher frequency region, so we are using LCR meter. This LCR meter will give the concept of inductance, capacitance, and resistance. So we call it impedance. So if you measure the impedance with respect to frequency, you'll get certain parameters. From that parameter, you can evaluate the dielectric constant. So this is the experimental setup for the LCR meter. This is the capacitance here, two metal plates. In between, I'm keeping the pellet. So based on the pellet dimensions are important. Before measuring the dielectric constant, make sure that the density of the sample is perfect. You should have more density. So complete a packed structure, you'll get the perfect dielectric constant. If there is a possibility, you can vary the temperature of the cell. You can determine the dielectric constant with respect to frequency by varying the temperature. Here, I'll show one of the instrument which I used for Nova control in the Hyderabad Central University. So this is the setup. This is a broadband electric spectrometer setup, which can operate it for 10 microhertz to the 20 megahertz region. This is the complete setup. Like previously, I've shown the capacitance layer. So where the sample is kept between the two electrodes, we are keeping inside. So this is a cryogenic chamber. So we can measure from 10 microhertz region to the 20 megahertz region. Once you get this particular data, what are the parameters you can evaluate from this? You can calculate the conductivity, you can calculate the modulus of electricity, modulus. Similarly, we can calculate the tan delta dissipation factor. These are all the parameters can be used to study the material characterization. Similarly, suppose I want to do with the any polymer like a gel sample. So here the interdigited electrode setup where you can keep the liquid cell like this. So it's like a honeycomb structure. The liquid is going to stay here. So this particular tray you have to keep in this particular area to measure the dielectric constant. But the major disadvantage of this particular electrode setup because it costs around $70 for one sample. So it's a more costly. So what we have done that this is replaced with a solid parallel material. So here I'll keep the liquid sample. I close the chamber. I made the two capacitors like this, top plate and down plate, where you can keep the liquid. You can close it. You can keep it between the two capacitor plates like a solid. You can measure the dielectric constant with respect to that particular frequency region. So with respect to this particular data, what you can calculate? You can calculate like relaxation, conductivity mechanism. Similarly, you can calculate the hardiness plot. From that, you can calculate the activation energies and glass temperatures, and you can vary the temperature. There are a number of functions which can fit to the particular data. You can evaluate certain parameters to study the material properties. So this is about the low frequency region. If we come to the microwave frequency region, we have three techniques. One is transmission line method, cavity perturbation method, and open-ended coaxial probe method. Each and every method have the advantages and disadvantages of the advantages and disadvantages when you're doing the measurement. The transmission line method, what I have shown to you here now, this is the transmission line setup because especially in engineering college you have X-band setup, that is the waveguide method. It consists of a klystron power supply, isolator which isolates the electromagnetic wave, the attenuator, you can calculate the frequency of the meter, and a slotted section. Here I'm taking the liquid sample here. To measure the electric permittivity of a liquid sample, at least you require 100 ml. By varying the thickness of the liquid sample, you can calculate the parameters. This graph shows the liquid permittivity measurements. If you look at the benzene is a non-polar medium, so you'll get the curve like this. By measuring the half wavelength between the two dips, you can calculate the permittivity. The same sample, instead of benzene, I keep a water, so it appears like this. Why this dip, the height is get reduced, the power is got reduced because the water is a polar material which takes the energy while rotating. So due to that, my energy goes on decreases. The same technique we can use it like this. So this is the incoming wave of electromagnetic wave. When electromagnetic wave is propagating through a material, its wavelength got changed. The same thing if you, in the case of polar material, if it is rotated like this. So because of the rotation of the dipoles, my electromagnetic wave energy is reduced. So there is an attenuation and there is a phase change. By with respect to the phase change and attenuation, you can calculate the permittivity properties. So this is the experimental setup. You can see in the laboratories, BTech laboratories. So klystron supply, and this is the isolator. This is a tuning setup. This is a sample cell. So this method is laborious method. You got to do for 6 hours to do the measurements. it takes longer time. Before the invention of this cavity perturbation and sensor method technology, people used to do work with J band. This is the X band setup. This is the Q band. The bands are different here, 30 to 36. And this is the free space techniques of E band. The same technique, we can use it for the solid samples. So if you keep the solid sample here, without keeping the solid sample, this black line shows the electromagnetic wave. If you keep the sample, it got shifted a little bit. How much change in shift? Based on the shift, you can assess the dielectric permittivity property of that particular frequency region. So because these waveguides are designed only for one particular frequency region, the J band, X band, P band, K band for discrete frequencies. So this is the setup for solid samples. So we have to cut the sample as per the dimensions. So this is one of the Teflon sample, and this is nothing but one ceramic sample, this cylinder sample. Like this, based on the dimensions, you have to prepare your sample holder. So this is the formulas. I can use it to calculate the permittivity at that particular frequency region. This is for solid samples. This is for liquid samples. The main advantage of this particular technique is you can operate for higher power capacities, and the cost is wise very less. The main disadvantage is, suppose I want to calculate the permittivity of a blood sample. So we can't use 80 ml blood sample there. So we need a certain sample which is a less than 1 ml. So this technique we cannot use it for to measure the properties of any biological liquids. Maybe you collect the water from the near to the tissues, maybe the liver, maybe the kidneys, maybe related to the corner, from the eye. If you take any liquid from that, we can't use this particular methodology to calculate the permittivity. So what is the best method to that? Here I'm using the cavity perturbation technique. What exactly the cavity perturbation technique is? This is the cavity which is resonates at one particular frequency. A cavity is nothing but a room which produces certain energy with respect to certain frequency. If you look at this particular figure, I'll try to demonstrate that how the cavity perturbation works. If you look at the cavity from the front view, this shows this designed for transverse electric TE mode of 107. 1 represents number of half period variation along x-axis, 0 represents y-axis, 7 represent along the z-axis. If you look at the front view, the electric field is maximum at the center. So the electric field is maximum at the center. This is the network analyzer screen. So this is my sample. So without sample, this is the frequency. This shows the frequency. If you insert the sample, there is a shift in the frequency. So based on the shift, we can calculate the permittivity and tan delta and dielectric loss. If this sample is filled with any material like a liquid, so resonant frequency got changed. Like this. So based on the smaller samples, maybe the thin rods, maybe the polymer samples, or maybe the any gel samples, we can measure the permittivity at this particular frequency region. This method cannot be applicable for high loss samples. It is applicable only for low loss samples. One major important for this particular doing the experiment is the dimensions of the sample is very much important so that you'll get error result. If the dimension is not proper, you may get the error results. So this method can be used to measure for thin film also. If any polymer is coated with the nano film, nano material, if you make it a proper slices, you can measure it. The thickness is important to measure about this particular methodology. So these are the formulas. You can use it for to measure the permittivity of the film samples or maybe liquid sample, maybe the solid samples, but not glossy materials. The next method, the major advantages is only small samples required. The disadvantages is we cannot use it for high lossy samples. And this is for only discrete samples. Suppose I want to measure the biological sample, yes, you can use it, but it not be lossy. So these are the cavities which I have designed in IIT Madras. The same samples I'm using in Hyderabad Central University. So these are different frequencies. So any faculty is doing measurements with the solid samples, maybe the liquid samples, maybe the films, you can consult me so that I can help you to characterize in this particular frequency region. The next method is a open-ended probe method. I'll tell you a simple example. This is the setup. This is the network analyzer. This is the source to produce micro frequency from megahertz region to the gigahertz region. This is the coaxial probe. We're sending the electromagnetic waves to the probe. We transmit it to the liquid medium, get reflected. From the reflected signal, you're getting the impedance. From that impedance, you're calculating the dielectric permittivity. So this is the principle of this open-ended coaxial probe method. This coaxial probe method, we are using the concept is called TEM, transverse electromagnetic wave mode. So in this particular network analyzer, we can operate for, in a central university, we have 67 gigahertz region. To study the impedance, we are using the Smith chart. So this is the Smith chart. So this is open and short. This is the inductance circles. The combination of impedance is nothing but R plus J omega C, or nothing but resistance plus reactance. So with respect to that particular data, we can measure the impedance of the sample. To explain a simple demo, to explain my concept, this is the port 1 and port 2. This is network analyzer, which consists of a Smith chart. When you connected a probe to open medium, you're getting the impedance like this. You're getting the point on the screen. This is the impedance. This is the open air. If this might block, this probe is blocked with the metal. If you take any metal, the reflection is more, so that you'll get the impedance in the opposite direction. It shows exactly 180-degree shift. So if you place the liquid, you can measure the impedance. From that impedance, you can vary the liquid sample, you can vary the temperature, you can measure all the properties. And one more important property here is, when you're doing the measurement of your sample, it should be calibrated. The calibration is more important when you're doing the experiment. You have to do calibration with open medium and air medium, with respect to the metal, with respect to known samples. Before doing the experiment, you should calibrate first up to what frequency you're getting the perfect response, and we can calculate. So to analyze the result, we have to use a lumped parameter model, two-port model. So based on that, you'll get the reflection, voltage standing wave ratio, then you can calculate. Sir, can I continue? Yes.
Just a moment, sir. We have got some network connection.
Okay.
So if you don't mind, can you please switch off your camera?
Yeah, fine.
For better browsing.
Okay, fine. 1 minute. 1 minute. 1 minute, sir. I'll do that. Is it okay now?
Just a moment, sir. We're working on it. Is everything fine on your side, sir?
Yes, sir.
Yeah, we are rejoining.
It's okay, sir. Can I continue?
Yes, sir. It's fine now.
Okay. So here, by using the calibration method, we can first do this. This particular methodology we can categorize for continuous range from 10 megahertz region to the 67 gigahertz region. We can measure for semi-solids and gels, liquids, films. The major important point you have to understand in this particular methodology is, as the frequency changes, the probe dimensions are going to be changes. So this particular method, we have 3 type of probes. We can, suppose you want to vary the temperature for higher temperature, especially for ceramic samples, we can use this particular device. Suppose I want to go for only liquids, moderately up to 100 degrees centigrade, I can use this particular. Suppose I want to go for further, maybe around above around 50 gigahertz region, I have to use this particular probes. As the frequency goes on increases, the cost of the cables also increases. Recently, we purchased this particular probe around 6.5 lakhs. This particular, especially this probe. Suppose you want to go for more than 50 gigahertz region, you have to spend around 16 lakhs for this particular slim probes. Recently, I have measured films also. As of now, no one reported this particular method using this solid sample. I had done the measurement with the Teflon. I got around 2.10 or 2.09. The reported value is around 2.12. So what I have done with a Teflon sample as well as the films. Initially, I had done with respect to films, I kept in between the probe and this particular dimension. I got the result. After that, I had done with the Teflon. So I have taken the data with the Teflon with the film also. I subtracted the dielectric data of Teflon. I got the film reflectance. So this is the dielectric permittivity of the films with respect to the frequency. So we're going to report this data to a journal. So this method can be used to find the dielectric permittivity, conductivity of a films, provided the thickness is important. The minimum thickness for this sample is half mm. So less than that we cannot work. Similarly, we tried with the high dielectric constant materials for ceramic, so it doesn't work. So this method is only works for a solids, semi-solids, gel samples, liquids, and films. So these are certain. Yeah. Hello. Hello.
Second.
Sir, is it okay? Sir, is it okay? Can I go further? Dr. Tinmal, is it okay? Can I proceed? Sir, I'm audible to you.
Sir, can you share your screen?
Sir, you can present.
Yeah. Is it okay now? Can I further? Can I go further? Thermal, is it okay?
Sir, you can share your screen and start the session, sir.
Yeah, already shared the screen. Are you able to see my screen now? Already have shared my screen. Is it okay? తిరుమల వినపడుతుందా? Now it is okay. Madam, is it okay now?
Yes, sir. Yes.
I'm getting a lot of noise, some disturbance in the signal. Can I go further? Tirmal, can I go further? Hello?
You can speak that out.
I'm audible right now. Can I share the screen now? Now, can I go further? Can I go further? Hello?
Please come to the picture, sir, without PPT.
Okay, fine. Okay, fine. Okay. So this is what you can measure the dielectric constant of any material by using the open-ended coaxial probe method. You can use it for solid samples, for thin samples, and gel samples. And when you're measuring the probe technique, the thickness of the sample should be around half mm. This is to be taken into the consideration. So this particular, after measuring the dielectric constant of different frequencies, if you plot the graph, you can able to observe that dielectric loss. Based on that, you can calculate the tan delta dissipation factor. From that, you can calculate the conductivity. You can analyze the relaxation mechanism at different frequency region. This broadband electric spectroscopy is one of the important tools, especially for a biological sample, to calculate the conductivity of the tissues, especially about the protein films. Based on that, that particular methodology can be used for to sense certain properties based on the conductivity. For an example, especially for the breast cancer detection, we are using this particular probe technique to evaluate the conductivity of healthy cell as well as the diseased cell. Based on that, we can able to identify what is exactly how much percent of the tissue got infected with the virus. So this is about my lecture talk. There is a disturbance. So I can able to show my particular results and conductivity mechanism of a biological cells. Thank you. If you have any questions, you can ask me now. I hope you enjoyed the session, the basic session, that you're able to understand what the importance of this microwave heating.
Right, students, it is the time to discussion. If you have any queries in terms of microwaves, dielectric materials, polarization. Sir,
If
I
any
have,
faculty,
sir, Vishnu,
okay,
sir,
fine. Yes, sir. Yes, sir.
Sir, I have one thought. In some of the materials,
Okay.
you see dielectric loss, especially in the range of about 45 degree to 65 degree or 75 degree like that. In some of the materials like glasses, ceramics, we don't observe that. Is there any particular reason for that? And again,
Actually, we are,
yes, sir.
sir. Here the thing is depends upon the how much polar about your compound. it is responding to that frequency or not. If you take the Teflon, which is low loss material, so we cannot get any loss spectra. Even you get, but the loss percentage is very less. Tan delta is very less. Suppose if you do with any water-based samples, you can observe the dielectric loss peak at more than you can repeat for 8 gigahertz region, 12 gigahertz region, 2.4 gigahertz region, and 18 gigahertz region. So it depends upon the your sample, especially about the, how much polarity of the compound.
Thank you, sir. And in slide number 42, I think so, there you have
Okay.
shown formula related to direct constant and dielectric loss. Can you explain formula, sir?
So
They are in terms of
slide number 40, yeah, I will tell you. Yeah, in that, especially in the formula, we are talking about the attenuation and phase factor, reflection coefficient. These are the three things related to the frequency. When your electromagnetic wave is passing through the material, one is attenuation factor, one is the phase change, similarly reflection coefficient and standing wave ratio, like scattering parameters. So based on my incident energy and reflected energy, how much amount of energy is lost. This energy law depends upon these particular parameters. That is the reason I'm focusing more on to obtain these particular parameters. Reverse calculation, we're calculating the dissipation factor.
one more, sir, last one. What is the applied voltage, sir, for that bigger
So
range
actually,
of frequencies?
we are applying minus 17 dBm, especially network analyzer. The input power is very less. It can vary from minus 10 dBm to minus 17 dBm. This is our input power range of in the microwave region. Because it's not like a microwave oven, that energy level is more, the power energy is level high, is only for frequency is more, but the power is minus 17 dBm, nothing but hardly 10 milliwatts of power, not more than that.
Thank you very much, sir. Yes, students.
Are there any questions from audience? Dr. T. Vishwam, sir, actually you presented well through interactive in terms of showing us the very simplest videos. It was fully connected with the subject content as well, and the whole content you highlighted the dancing equation terms and that how well they are connected with the phenomenon as well. It was really thought-provoking and truly fundamentally connected with the basic concepts of physics as well. Thank you so much for the wonderful presentation, sir. Thank you for joining us.
Thank you for inviting me such a good seminar. Actually, because of net connection, I was not able to show the one proper result. I'm doing for the kidney tests, the kidney stones. I'm doing the work with the kidney stones. Myself and Tirumali are working on kidney stones. So we are going to analyze from your mobile phone that we're able to see that the stone size also.
Trying to see the
Thank you. Thank you. Thank you.
Really wonderful. Really wonderful. Thank you once again, sir.
Thank you, sir. Thank you.
Please we can wind up the session, sir.
Can I my screen? Can I? Okay, fine.
Yeah, you can wind up. Yeah.
I thank Dr. Dept sir for sharing the session. Thank you, sir.
Thank you, sir.
Thank you, students, for attending the session. Tomorrow also we'll be having wonderful sessions. And one important thing is the sessions will be there once in a semester or maximum twice in a semester. So whenever there is an opportunity